Good morning, students. Today we will study about the electric field due to a surface charge distribution. In the previous class, we already studied about the electric field due to a line charge distribution. Now, today we study about electric field due to a surface charge distribution. When the charge is uniformly distributed on a surface, then the force on vanishingly small test charge q naught placed at a distance of small r is given by F is equals to k q naught surface integral sigma ds divided by r square r cap. This is according to the Coulomb's law. Now, if the charge is located at position r, then force due to the surface charge distribution is given by F is equals to k q naught surface integral sigma ds divided by modulus of r minus r dash whole cube into r minus r dash. And here sigma is surface charge density. In the previous class, in the case of linear charge distribution or line charge distribution, there was lambda, the linear charge density. But here sigma is surface charge density, and r dash is position vector of the elementary charge having ds of the surface charge. Now, electric field is defined by E is equals to limit q naught tending to 0 F divided by q naught. This is the formula for electric field. And if we put the value of F, then we get E is equals to K into surface integral sigma ds divided by modulus of r minus r dash whole cube into r minus r dash. This is the electric field due to a surface charge distribution. Now, our next topic is a dipole in non-uniform electric field. We already studied about a dipole in uniform electric field. Now, if a dipole is placed in a non-uniform electric field, then what happens? When a dipole is placed in a non-uniform electric field, then the force acting on the two charges of the dipole are not equal in magnitude and their directions are not exactly opposite to each other. If the length of the dipole is very small, means if dipole is short, then the force acting on the two charges of the dipole will be equal, and this time the torque act on the dipole is given by tau is equals to P cross E. Tau is equals to P cross E. This is the torque. And here E is amount of electric field at the center of the dipole. Now, this is the diagram which is representing that a dipole is placed in non-uniform electric field. At point B, where positive charge is placed, the electric field values are Ex dash, Ey dash, Ez dash, and at point A, where minus q charge is placed, the electric field's components are Ex, Ey, Ez. These are the three components of the electric field. And at point B, the electric field components are Ex dash, Ey dash, Ez dash. Now, since dipole is placed in a non-uniform electric field, so it will experience a net translatory force in addition to the torque. There will be a net translatory force. Now let the components of the electric field along x, y, z directions at point A are Ex, Ey, Ez, and at point B are Ex dash, Ey dash and Ez dash respectively. So the electric field value or x component of the electric field at point B, Ex dash is equals to Ex dash is equals to Ex plus Dex. Now Ex dash is equals to Ex plus del Ex by del x into dx plus del by del y Ex dy plus del by del z Ex dz. This is the first equation. Let the component of the force along x, y, z direction at point A are Fx1, Fy1, Fz1, and at point B these are Fx2, Fy2, Fz2 respectively. So the net force along x direction acting on the dipole is given by Fx is equals to Fx2 minus Fx1, Fx2 minus Fx1, and this will be equal to Q into Ex dash minus Q into Ex, and Fx will be equal to Q into Ex dash minus Ex. Now we can find the value of Ex dash minus Ex from the equation first, and if you put this value in the above equation for Fx, then we get Fx is equals to Q into del Ex by del x into dx plus del Ex by del y into dy plus del Ex by del z into dz. And if the components of the dipole moments along x, y, z directions are given by components of the dipole moment along x, y, z directions are given by Px will be equal to Q into dx, Py is equals to Q into dy, Pz is equals to Q into dz. And now if we put the value of Q into dx, Q into dy, Q into dz in the equation 2, then we get Fx is equals to Px into del Ex by del x plus Py into del Ex by del y plus Pz into del Ex by del z. And we can arrange the equation as Fx is equals to I cap Px plus j cap Py plus k cap Pz dot I cap del by del x Ex plus j cap del by del y Ex plus k cap del by del z Ex. And if we write this equation in terms of the gradient, then we can write Fx is equals to P dot del Ex. Similarly, if we write the similar equations for yz component of the f, then we can write Fy is equals to P dot del Ey, Fz is equals to P dot del Ez. Now, the total translatory force experienced by a dipole in a non-uniform electric field is given by F is equals to I cap Fx plus j cap Fy plus k cap Fz. Put the values of Fx, Fy, Fz in the above equation, then we get F is equals to I cap P dot del Ex plus j cap P dot del Ey plus k cap P dot del Ez, and finally we get F is equals to P dot del Iex plus je I cap Ex plus j cap Ey plus k cap Ez. F is equals to P dot del I cap Ex plus J cap Ey plus K cap Ez, and we can write it F is equals to P dot del E. This is the total translatory force experienced by a dipole in a non-uniform electric field